Hello and welcome to this clip going through the Chemistry Olympiad Round 1 paper 2005 question 3. So this question is about methanoic acid, and specifically the fact that it's found in the sting of an ant. So it's associated with weak acid chemistry, so it should be applicable for second years rather than first years, because it brings some of the Ka and pH calculation work in that is covered in the second year. So in every single Chemistry Olympiad question, you'll have a couple of paragraphs at the beginning that give you a context and set the scene for what the chemistry that you're going to be tested is going to be like. And it's always useful to have a read of it, not just to get your mind thinking about the context of the question, obviously, but also to see if there's any data that might be useful. So for example, in this case, if you look at the second paragraph, you can see what I mean. So it might be worth keeping an eye on this for later on in the question. So the first part of this question talks about how much an ant actually injects you with. So it says in the second paragraph we just referred to that a typical ant may inject around 6 times 10 to the minus 3 centimeters cubed of their solution. So what you've got to do is work out the total volume of pure methanoic acid that's contained in a typical ant. So if we work through the maths systematically, we take one injection as 6 times 10 to the minus 3 centimeters cubed. We're told that this is 50% by volume of methanoic acid, so we divide this by 2 to get the amount of pure methanoic acid present in that one injection. If that one injection is 80% of the total methanoic acid the ant has in its body at any given time, you can divide that by 0.8, or 80 over 100, which gives you 3.75 times 10 to the minus 3 centimeters cubed of methanoic acid. So the next part of question A asks you to calculate how many typical ants, so in other words, how many of this particular ant would have to be distilled to produce 1 decimeter cubed of pure methanoic acid. So that would mean you'd need 1,000 centimeters cubed of pure methanoic acid. So that gives us 1,000 centimeters cubed divided by the volume in one ant. So that means we'd need 266,667 ants. It's actually 266,666.6, but obviously you don't get 0.6 of an ant running around in nature. So I've rounded it up to take care of that. So the first part of part B just asks you for a simple equation between a hydrogen carbonate and a carboxylic acid. So taking our first year chemistry of hydrogen carbonate with acid giving you salt, carbon dioxide and water, it's quite straightforward to put that together. They don't ask for state symbols in this case, so you don't need to give it. So if we're working out the mass of HCOOH per injection, we have to think about the fact that each injection is 50% by volume. So converting density and volume into mass means you multiply density times volume, and then you have to divide the volume by 2 because then you're taking into account the 50% of methanoic acid by volume. So that gives us 3.6 times 10 to the minus 3 grams, which when divided by the molar mass of methanol gives us 7.8 times 10 to the minus 5 moles. Sorry, not methanol, methanoic acid. So it gives us 7.8 times 10 to the minus 5 moles of methanoic acid. So the final part asks you to calculate the mass of sodium hydrogen carbonate that would be needed to neutralize completely the sting from this ant. So considering that they've got a 1-to-1 mole ratio, you can multiply the number of moles of methanoic acid by the molar mass of NaHCO3, which gives us 6.57 times 10 to the minus 3 grams of NaHCO3. Okay, so moving down to part C this time. So what we're trying to do is work out the concentration of methanoic acid. So the concentration of methanoic acid is the moles of methanoic acid over the volume of the solution formed, which is, as the question says, 1.0 centimeters cubed. So therefore, if you divide those two together, that gives you 7.8 times 10 to the minus 2 moles per decimeter to the minus 3. So part D wants us to work out the pH of the methanoic acid. So pH is minus log of the hydrogen ion concentration, so rearranging that so that H plus concentration is the subject, it gives you 10 to the minus pH. So therefore we do 10 to the minus 2.43, which gives us 3.72 times 10 to the minus 3 moles per decimeter cubed. So in part E, they want us to work out how much of the original HCOOH has actually ionized. So you take the concentration of your hydrogen ions that you've just worked out and express that as a percentage of the original 7.8 times 10 to the minus 2. So that gives us 4.77%. So if we think about the HCOO minus ion, which is also produced during the dissociation, they're in equimolar proportions, so therefore you can take the hydrogen ion concentration and square it. Then you don't have to worry about the HCOO minus. So that goes on top of your Ka expression, and what goes on the bottom is the remaining HCOOH. So if we take the original HCOOH concentration, 7.8 times 10 to the minus 2, and subtract from that the amount that turned into hydrogen ions, which is 3.72 times 10 to the minus 3, that gives us our denominator. So that gives us 1.86 times 10 to the minus 4 moles per decimeter cubed. So that takes us to the end of this clip, which takes you through the basics of weak acid behaviour. Really good for practice at year 2, and actually considering, again, not too bad for first year as well, even though you don't do this kind of stuff until your second year. I think now, having had a look through the question, there's probably enough information to guide you through without having to have gone away and studied it separately. Okay, so once again, thanks for listening, and until next time, see you soon.